With the flight of spacecraft number 7 in the MR3 mission, Project Mercury had successfully integrated man with the Mercury systems in spaceflight. Upon completion of a thorough post-flight inspection, the final phases of the suborbital ballistic flight program was scheduled. The spacecraft and its systems had been further qualified for the next segment of the overall Project Mercury mission, orbital flights. Through research and development, modifications in production spacecraft continued during this report period. Early in July, at Cape Canaveral, testing of an explosively actuated side hatch continued. This hatch will permit rapid access to an injured astronaut from outside the spacecraft. It also provides for rapid egress for the test pilot should an emergency develop. The astronaut assigned to pilot the MR4 mission observed the testing and pre-launch preparations. 70 quarter-inch titanium bolts secure the hatch to the spacecraft sill. A 6/1000th of an inch hole is drilled in the bolt head to provide a weak point. Between the inner and outer seal, a mild detonating fuse is installed. When ignited, gas pressure between the seals causes the bolts to fail under tension. This hatch will be used for the first time on the spacecraft in the MR4 mission. The astronaut can detonate the hatch from within, or Recovery Forces personnel may do so through the use of an external plunger. Development and testing of an auxiliary flotation device continued in July and September. Designed to provide spacecraft stabilization in moderate open sea environment for 72 hours, the device will be deployed by aircraft. In contingency recovery situations during the orbital missions of Project Mercury, pararescue personnel will attach the collar to the floating spacecraft. From information gained in these tests, operational versions of the device will be delivered. The ballistic flights qualified the Mercury system capabilities on brief space flights. Engineers and technicians continue to test the spacecraft under simulated orbital conditions. Here at the McDonnell Aircraft Company High Altitude Chamber, spacecraft number 10 has been used in Project Orbit. This program can determine if system deficiencies exist and inherent design problems can be identified. Mercury Atlas profiles have been simulated with major emphasis on the manual attitude control system. Its ability to operate under the combined pressures and temperatures experienced in orbital missions has been checked out. All systems have been tested at simulated altitudes varying up to 250,000 feet in this large plastic tent. By the end of July, approximately 50% of this evaluation program had been completed. The Mercury Scout 1 payload, which will test the ground network's tracking and communications capabilities, was undergoing pre-launch monitoring of all systems. Here at Aeroneutronics, a division of the Ford Motor Company, the payload to be boosted into an elliptical orbit by a Scout rocket was readied for checkout. Mercury communications and instrumentation components are housed inside the rectangular-shaped outer structure. Systems are automatically checked and monitored by this checkout console. The payload is designed to repeatedly test the real-time orbital computing data at the Goddard Space Flight Center and the extent of systems errors at radar sites. Radiation horns will acquire data for analysis concerning attenuation of radio frequency signals. Vibration tests simulated normal and transverse longitudinal stresses. Liftoff and powered acceleration simulations were conducted, testing the payload's capability to transmit telemetry data during flight. Extensive tests under probable pressures to be experienced in orbital flight were also conducted. The payload's guidance and control capabilities were tested for both regulated and unregulated pressures, from 0 to 600 pounds per square inch absolute under regulated conditions, and up to 3,000 pounds per square inch unregulated. With initial tests concluded and checkouts complete, the payload was shipped to Cape Canaveral. Early in August, the oxygen flow sensor in the environmental control system underwent a series of development tests. A check valve has been added to the sensor to prevent loss of cabin pressure in the event the snorkel inflow valve opens during flight. The sensor valve was subjected to vibration rates varying from 20 to 20,000 cycles per second. With the modifications successfully completed, spacecraft systems are being changed to meet specifications. Also at McDonnell, heat shield hot release mechanism tests were conducted. Technicians checked the recording and control instrumentation equipment. Prior to testing, the release system was operated at room temperature. Then the clamp ring area was heated to re-entry temperatures for 15-minute periods. While recording and instrumentation data were being observed, the lamps were turned off. The heat shield was allowed to cool to normal pre-impact temperature, and the release mechanism was actuated, permitting the shield to drop and extending the impact skirt. As Project Mercury enters the orbital mission phase, the progress in research and development has set the pace for overall project advances. By the end of July, spacecraft production work was nearly completed. Spacecraft systems modifications were minor in nature and would not cause any major delays in spacecraft production. All of the remaining Mercury spacecraft were in the White Room, being readied for systems tests, undergoing these tests, or being prepared for shipment. With Atlas adapter number 20, construction of the adapter rings was nearly finished. Under immaculately clean White Room conditions that ensure quality control, adapter number 16 will be ready for installation when electrical wiring of components is completed. Practically all escape tower pylons were complete, and installation could be made as each spacecraft is completed. The final spacecraft under contract, number 20, was undergoing modification of electrical circuitry to incorporate added instrumentation to meet latest design requirements. As spacecraft number 19 approached completion, insulation was fitted around the hydrogen peroxide fuel storage tanks for the automatic stabilization control system. Components which had been installed were inspected at the junction of the recovery compartment. Interior instrument panel wiring would bring this spacecraft to final configuration. Miniaturized circuitry panels were fabricated and reworked in accord with new instrumentation requirements. Components were soldered, cleaned, dried, and installed on an accelerometer panel. Similar work was conducted on one of two panels in the events mixing circuit, utilized in spacecraft number 18 and 19. The reaction control system's attachment fittings were inspected on spacecraft 17's bulkhead as it neared completion. A major subassembly, the antenna fairing, was installed on spacecraft number 15. A small pressure bulkhead was checked and prepared for installation prior to cabin checks for leakage. With bulkhead and retro-rocket package in place, the spacecraft rapidly approached delivery configuration. Spacecraft number 13 was prepared for delivery. Final installation and inspection of the recovery compartment was made. The heat shield had been installed and a striped retro-rocket package attached. Awaiting data evaluation from the scheduled unmanned and primate orbital Mercury mission, this phase of the Mercury project will rapidly reach completion. In less than 3 years, McDonnell will have delivered 20 complete production spacecraft, their adapters, escape towers, and retro-rocket packages. The task of the Atlas to insert a spacecraft into an orbital flight mission will be expedited through continued efforts in the development and production of launch vehicles. Of the 7 booster vehicles in production, 3 are scheduled for flights this year. Launch Vehicle 109D, scheduled to boost the free world's first manned orbital spacecraft into orbit around the end of this year, was nearing the checkout stage of production. A newly modified astronautics programmer was fitted. As technicians trace wiring, the big launch vehicle nears completion and will undergo composite testing. Following these, acceptance tests will be conducted before delivery to Cape Canaveral. Undergoing composite tests was Mercury Atlas production model 93D. During these tests, every complex system in the launch vehicle undergoes intensive examination. Simulated flights are programmed and the mission results are monitored. During this phase of testing, the booster engines are gimbaled, just as they might be during the liftoff and insertion phases of powered flight. Production models 103D and 119D, both destined for use in Project Mercury flights, were in the decontamination building. This cleansing process is part of the quality control measures stressed throughout the Mercury program. First, the booster fuel tank is scrubbed with scalding hot water and detergent. Then, a thorough rinsing and a bath of trichloroethylene. This compound loosens microscopic hydrocarbons and other particles which, if left in contact with liquid oxygen, could cause a failure in the fuel system. The tanks are then rinsed with deionized water. After a thorough wiping down by specially trained technicians, the tanks are pressurized and sealed to protect them until pre-launch fueling. Mercury Atlas Vehicle 88D had been completed. Project Mercury had accepted it for the MA4 flight test, scheduled to evaluate the orbital capability of the Mercury spacecraft. As the booster was loaded aboard the C-133 transport for delivery to the Atlantic Missile Range at Cape Canaveral, Project Mercury was preparing all elements of the MA4 flight mission. The Atlas, the worldwide network of ground tracking stations, the recovery forces, the spacecraft itself. This flight would begin the new phase of Project Mercury, and the success of the flight would advance the probable flight of first a primate and then a manned orbital spacecraft later this year. All 7 astronauts participated in various training procedures to attain familiarization with Atlas orbital missions. For man's purposes in space exploration could not be achieved without continuous astronaut training. The procedures trainer at Cape Canaveral was used extensively. Atlas flights were simulated, including planned mission abort procedures and emergency re-entry profiles. The training simulation is programmed through this control panel, and the instructor, acting as the Mercury Control Flight Director, can inject emergency profiles as technicians observe and evaluate the astronaut's correction of a simulated systems malfunction. The training sessions conducted at this time were devoted to the Mercury Atlas countdown and launch profiles, as well as attitude control maneuvers of simulated orbital flights. The 4th Human Centrifuge program was conducted during this period. All 7 astronauts participated in the simulated orbital space flights. Control data on each test pilot's physical capabilities to be compared with actual in-flight performance data was gathered for evaluation. Medical sensors were attached to astronaut Shepard's body. These sensors record pulse, respiration, and body temperature data and require exacting application. During this training exercise, a new blood pressure measuring device was used by astronaut Shira. This sensor was undergoing final qualification testing in the centrifuge trials, recording information from straining movements during orbital flight profiles. Mercury test pilot Slayton, with all biomedical sensors in place, begins suiting up. The operational pressure suit is an integral part of the environmental control system. As astronaut Glenn's suiting up nears completion, special attention is given to the fitting of the neck collar to ensure positive ventilation throughout the suit. When fully suited, as astronaut Carpenter is here, the Mercury test pilot is provided with protection against cabin decompression in flight. The suit operates as a separate oxygen supply, should an emergency develop. All flight helmets, the same as astronaut Cooper's, incorporate two-way voice communications equipment and a buffet protection liner that safeguards the space pilot from acceleration, deceleration, and impact forces. Fully suited, each test pilot took his turn in the simulated orbital missions, as astronaut Grissom does here. This program provided training in all normal launch and re-entry profiles, as well as most Atlas abort sequences. During these tests, any significant changes in the astronaut's physical condition and operating capabilities are noted. Qualification trials were programmed by punched tape. This program, at Johnsville, Pennsylvania, provided the astronauts with practice in straining techniques. Emphasis was placed on the retention of good vision and consciousness under high Atlas re-entry G loads. Medical monitors appraised the physical hazards the Atlas accelerations imposed on each astronaut. The various G forces expected during launch, separation, and re-entry were simulated. electrocardiogram traces supplemented the physiological data transmitted by the various body sensors. Through this simulator console, the engineer brings about a tumbling procedure at maximum dynamic pressures. This maneuver simulates an abort situation where the astronaut could experience from plus 10 G to minus 10 G in 1 second. Each of the astronauts gained additional primary training advantages in the centrifuge program, developing techniques for breathing and speaking under high G acceleration forces in preparation for manned orbital flights around the end of this year. To provide real-time data between the Mercury Control Center and the spacecraft is the task of the Mercury Network. During each countdown, launch, and flight, some 15 flight controllers observe these data consoles at the Mercury Control Center. As liftoff time nears, direct communications between the flight director and the duplicate Mercury Control facility at Bermuda is maintained. Bermuda's proximity to the flight path provides the vital acquisition and telemetry data, essential during the critical 20-second period at engine cutoff. This data is instantly transmitted to the data reduction and computation equipment at the Goddard Space Flight Center, which advises the Mercury Flight Dynamics Officer at Cape Canaveral of the trajectory, altitude, attitude, the range and azimuth of the spacecraft. Nicknamed FIDO for short, he must correlate all this data, plus considering the Goddard computer's recommendations, and decide whether the mission is abort or go. And the network monitor instantly communicates the decision by direct voice contact to all stations scattered along the orbital flight path as they track the spacecraft and evaluate the data they received in real time for further flight progress determinations. On August 13, contractors, NASA, and Goddard Space Flight administrators met here at the Mercury Control Center. The entire network had been thoroughly tested, and 4 stations had actively participated in the suborbital flights in May and July. The tracking and ground instrumentation system, called TAGIS for short, was formally accepted by NASA, and the operational aspects of this vital link in the Mercury program were delegated to the Goddard Space Flight Center for future orbital missions. With 3 successful suborbital flights now history, Project Mercury scheduled a second manned ballistic spaceflight in July. This flight would advance the qualifications of the spacecraft and its systems and further evaluate man's ability to perform in flight as a functional unit in Project Mercury's flight program. On the 1st of July, spacecraft number 11, symbolized Liberty Bell 7, was transferred to Launch Pad 5 at Cape Canaveral. For about 60 days prior to liftoff, astronauts Grissom and Glenn participated in the specific mission preparation for the MR4 flight. Experience gained during the build-up shapes the Mercury test pilot's pattern of in-flight actions and responses. The spacecraft movement up the gantry was observed. Once inside the green room atop the gantry, the spacecraft was mated to the Redstone launch vehicle. Astronaut Grissom participated in the post-mating inspections and systems checkout. On July 5, the escape tower was mated to the spacecraft. And in the blockhouse, various segments of the countdown procedure were observed, where during the final 2 minutes prior to liftoff, an astronaut will be in direct voice contact with the Mercury test pilot. During insertion practice on July 6, a countdown to T-minus 45 minutes was conducted to obtain physiological data. This practice assisted astronaut Grissom in specific spacecraft orientation. Emergency pad rescue training sessions were conducted in anticipation of the possibility of an emergency prior to the gantry's removal. The astronaut can escape injury in an emergency after the gantry's removal through the use of the cherry picker. Marine helicopters assigned to the Mercury recovery operation practiced spacecraft retrieval during this pre-launch period. In preparation for the MR4 flight, Grissom flew 100 Redstone mission profiles in the Mercury Procedures Trainer. His condition and proficiency were observed and monitored for later comparison and evaluation. 6 simulated missions with astronaut Shepard as the spacecraft communicator were conducted, integrating Mercury control personnel. These missions included countdown, liftoff, and in-flight procedures. Complete flight readiness had been achieved, and the launch was scheduled for the next morning. Late in the evening of July 17, marginal weather forced postponement. Familiarization with land masses would aid the pilot in making observations through the new, larger spacecraft window. Insertion was accomplished on the morning of the 19th, and the countdown proceeded. At T-minus 10 minutes, the unfavorable weather caused the flight to be scrubbed. Astronaut Grissom had spent 4 hours in the Mercury spacecraft. The flight was rescheduled, and preparations were again being made on the evening of July 20. The Redstone launch vehicle was fueled with the liquid oxygen it uses to develop more than 78,000 pounds of thrust. The fueling was completed at approximately 3:35 a.m. The Redstone and the Mercury spacecraft were ready, and the Mercury test pilot arrived from Hangar S about 20 minutes later. Once again, he rode up the gantry elevator. As the countdown proceeded without incident, the vexing weather situation caused a hold to be called. At T-minus 9 minutes, the gantry was pulled back for the final time. The cherry picker was raised into position. The countdown was nearing completion. Downrange, the recovery ships were stationed in a line along the flight path and in the planned landing area. As the countdown neared its final seconds, the recovery helicopters were airborne. Inside the blockhouse, astronaut Slayton advised Grissom of countdown events and communicated commands from T-minus 2 minutes to liftoff. Seconds prior to launch, the umbilical cord disengaged, and at 7:20 a.m. on July 21, the free world's second manned suborbital Mercury flight was airborne. Inside the Mercury Control Center, astronaut Shepard verified Grissom's condition and systems reports and advised the test pilot of pitch and trajectory disposition. The fuel system was go. Grissom was experiencing 1 1/2 G. Cabin pressure was 8 pounds per square inch, and the oxygen system was go. All systems were go. The flight surgeon maintained close observation of the test pilot's physiological status as the flight progressed. Grissom's electrocardiograph showed no abnormalities. His heartbeat, respiration, and body temperatures were within the expected tolerances. At engine cutoff, the spacecraft made its turnaround, and the astronaut was now weightless. The environmental system was monitored in the control center as the astronaut reported his cabin pressure holding at 5.5 pounds per square inch. Suit pressure was good. The flight's progress was charted on the plotboards. The spacecraft position, as well as the probable landing point, were observed on the world map, as the spacecraft communicator verified the astronaut's report that the drogue was green, the main chute was reefed. Airborne search aircraft using radar homing devices were able to provide a fix on the Liberty Bell 7 when the Sarah beacon started transmitting at main chute deployment. Visible to the recovery forces before impact, the landing appeared normal. The reserve chute had been jettisoned. The retrieval helicopters were within 2 miles of the landing point. Grissom indicated he would be ready for pickup after completing post-flight instrumentation checks. As the lead helicopter moved in to hook onto the recovery loop, premature actuation of the side hatch detonator occurred. Grissom was forced to leave the rapidly filling spacecraft. The recovery helicopter struggled with the almost submerged craft. In the attempt to lift the water-filled craft, the helicopter's lift capabilities were overtaxed by about 1,000 pounds. The second recovery helicopter moved in to pick up the astronaut. Grissom was obviously having difficulty maintaining flotation and was being buffeted by waves and by helicopter rotor wash. After 4 anxious minutes, Grissom struggled into the horse collar and was lifted clear of the water. When an apparent malfunction occurred in the lead helicopter's motor, the spacecraft was jettisoned. It sank immediately on release from the helicopter. Just 35 minutes after liftoff, flying a little farther, a little higher, and a bit faster than his predecessor, astronaut Virgil I. Gus Grissom appeared to be in good spirits, although wetter than programmed. As President Kennedy congratulated Grissom, it was determined that the second manned suborbital flight had reached an altitude of 118 miles, had traveled at approximately 5,280 miles per hour, and 303 miles downrange. Anxious medical officers removed the spaceman's pressure suit, paying close attention to the new neck dam collar, which kept the water from pouring into his suit. Atlas production model 88D, to be used in the first unmanned orbital Mercury flight, was erected on July 18. The refurbished spacecraft, successfully aborted in the MA3 flight and now designated 8A, was carried to the gantry and mated with the Atlas on August 4. This flight would test the orbital capabilities of the spacecraft and its systems, further qualify the Atlas booster for Mercury missions, and test the tracking and ground instrumentation acquisition and transmission capabilities. Launched on September 13, the MA4 flight was to fly one orbit before the reentry procedure was to be initiated near the command control station in West Mexico. Inside the Mercury Control Center, the flight director managed the flight and the network operation. The Bermuda Center verified the trajectory. The tracking and acquisition facilities of TAGUS were functioning as programmed. One test objective was met early in the flight: the ability of the Atlas to release the spacecraft into proper orbit. As the spacecraft successfully completed the turnaround and was flying in the orbital attitude, Mercury control personnel observed the various systems data and verified that all systems were go. The spacecraft communicator was in direct voice contact with the tape recorders aboard the flight vehicle. As the spacecraft, with its crewman simulator, passed over Africa just 17 minutes after liftoff, all systems were go. The Environmental Control Systems console registered cabin and suit pressures and oxygen consumption data. 62 minutes after launch, the spacecraft, traveling at more than 17,000 miles per hour, passed over the Australian tracking stations. The onboard timer commanded retro fire at T plus 89 minutes as the spacecraft approached the west coast. The reentry procedure was initiated, and the spacecraft encountered the Earth's atmosphere approximately 300 miles east of Savannah, Georgia. The probable impact point indicator operates on separate individual electrical circuits by the Goddard computers. 1 hour and 49 minutes after launch, spacecraft 8A landed in the programmed landing area 200 miles east of Bermuda. It had reached a maximum altitude of about 140 miles. All test objectives were considered to have been met. The USS Decatur retrieved the spacecraft 82 minutes after landing. Complete post-flight inspections of the spacecraft and data evaluations of all the mission elements were underway as of the close of this report period. The Mercury Scout 1 flight has been scheduled for early November to gain additional network operational testing. The payload of Mercury communications equipment will provide signals for the tracking sites to acquire, track, and communicate to evaluate overall systems efficiency. The 4-stage Scout rocket measures approximately 70 feet in length and weighs 36,000 pounds at liftoff. On July 27, the solid-fueled test vehicle was erected on Launch Complex 18B and placed on a standby condition for launch. The production spacecraft to be used in the first 3-orbit Mercury mission later this year has been delivered to Hangar S. It is presently being readied for the Mercury Atlas V test. Designated spacecraft number 9, systems tests were begun on September 15. Later, it was placed in the high-altitude chamber for simulated pressure and temperature tests. Tested at altitude simulating orbital temperatures and atmospheric pressures, systems deficiencies can be determined during these tests. On August 25, the Primate, to be the test subject on a 3-orbit mission, arrived at Cape Canaveral from Holloman Air Force Base. In this specially designed support couch with an advanced psychomotor tester, pallet and water feeder, and the new blood pressure sensor, the 40-pound chimpanzee was placed inside spacecraft number 9 in the altitude chamber. Orbital flights were then simulated, providing baseline data to check with in-flight data. During this 6-week pre-flight preparation period, the test subject will participate in various other tests. Each test will provide a reference profile for later comparison and evaluation. With the successful completion of 2 manned suborbital flights, Project Mercury completed a major phase of the overall program. The successful orbital flight of an unmanned Mercury spacecraft, the evaluations from systems operation provided by the Mercury network, and the successful recovery of the spacecraft constituted another major step forward. All these steps, from research and development through flight test, and the preparation for scheduled flights in the near future, bring Project Mercury closer to its ultimate goal, manned orbital flight.